Welcome to Fred
and Amy's Math
Math
Shack.
Our topic today is tangents and normals, and I've got a question for you. Which of the following is true? A, B, C, or D? I want you to have a read of these, pause the video, and then think about it. If you're not sure and you've forgotten what some of these things are, then I'll give a quick recap. Okay, so if I have a function, and I'll draw it on a graph like this. Okay, maybe it's a cubic, maybe it looks a bit like that, or another function that looks a little bit like a cubic. The instantaneous gradient is the momentary gradient as I move along the curve. So I can see I've got a positive gradient, and then it becomes 0, then it becomes negative, and then it becomes 0, and then positive again. I could actually work out the gradient at a specific point, and that would be the instantaneous gradient. A tangent at that point is a line that just touches it, and then a normal, just like with circles, is a line that is at 90 degrees. So see if that helps. What do you think the answer is? Well, the answer is D. The value of dy by dx, this is the instantaneous gradient, but in terms of x, is the instantaneous gradient at that point. So if I have a cubic, I find dy by dx, and I let x equals 5 or something, it gives me the gradient at x equals 5. So that one's fine. The value at dy by dx at a point is the gradient of the tangent at that point. Well, although we had this method for finding out dy by dx, where we actually had 2 points and we brought them closer and closer together, it's equivalent to finding it gives us the gradient at the point, and the tangent will also, because it just glances off, actually it does have the same gradient as the instantaneous gradient at that point. So B is correct as well. And finally, negative reciprocal, that's when you have a gradient and you do minus 1 over m. So if the gradient of the tangent is m, the negative reciprocal will be minus 1 over m. And in fact, yes, because they're at 90 degrees, this is exactly right. If you find dy by dx at a point, and then you do minus 1 over it, you'll get the gradient of the normal. So that one's true as well, and you can see that leaves us with D. What that means is that if we can find dy by dx, we can evaluate it at a point, and we can get the gradient of a tangent. We can do the negative reciprocal and get the gradient of the normal. And from that, we can get the equation of the tangent and the normal. So now that I've given a just introduction to this lesson and tried to link in dy by dx with tangents and normals, have a go at this question. What do you think the answer is? To get the gradient of the tangent, we need to find dy by dx. That gives us instantaneous along the curve. If we remember our rule, we multiply by the power, so it's going to become 15, and we reduce the power, so the first term becomes 5x cubed. Sorry, 5x cubed becomes 15x squared. We know that if we're adding terms, we can just differentiate them separately. The minus 12x becomes minus 12. This is a special case. We just get rid of the x. That's dy by dx. That's everywhere along the curve. So if we want it at the point 1 minus 7, we substitute in x equals 1. dy by dx then equal 15 times 1 squared, that's just 15, minus 12, and we're going to get an answer of 3. So well done if you got that. If you weren't sure, I hope that it makes sense now. I'm just going to bring out one other little bit of notation at this point. I might call my y a function, 5x cubed minus 12x. I have already spoken about this. Then f dash x would equal 15x squared minus 12. And the nice thing about this notation is I can then straight away substitute in a point. If I want to put in 1, then I write f dash 1 equals 3. So that's another way of me writing this. So you can see it's actually a bit advantageous because it does it all really concisely. Okay, you'll see both used, but I will be using this later in the lesson. How about this one then? A curve has equation 2x squared minus 5x plus 3. What's the gradient of the normal at x equals 2? Have a think. So again, we're going to have to find out dy by dx. It's going to be 4x, because I multiplied by the power, reduce the power, but I don't write the 1, just 4x. This becomes minus 5, and I get rid of the constant. The normal at x equals 2, well, first of all, we need to find out dy by dx when x is equal to 2. And this time I'm going to substitute in 8 minus 5, it's going to be 3. So this is the tangent gradient. And the normal gradient is then the negative reciprocal it's going to be minus 1 over 3. So it is B. If you've understood that, then you are well on your way to be able to accomplish this lesson, because the only extra step we're going to take now is, once we've got the gradients, we're going to have to work out the equation of the line. But we've studied straight lines, so it's going to be a recap on that. Right, let's see this method in action. You are more than welcome to pause this video and have a go at these questions and then look back after. I've talked about how you can get the gradients of the tangent and the normal. Previous lessons, we've looked at how to work out the equation of a line if you have coordinates and the gradient. So actually, this is just going to be implementing both of those. But I'm going to go through it now if you want to check or if you're not sure. Right, find the tangent and the normal. It means the equation. It doesn't actually say, but find the equation of the tangent and the normal to this curve where the x coordinate is 0. Okay, I've given you the graph. You wouldn't always be given the graph, but this just helps, I think, visually look at what's happening. And I'm just looking at I don't think it's quite like that actually. I'm just looking at the line that glances off of the curve at x equals 0. So this is going to be the normal, sorry, the tangent. And that's the equation that I want to find. And I will put on the normal at the same time. So that's going to be perpendicular to the line. Remember, it also goes through x equals 0. So there we go. And we've got this 90-degree angle. Okay, now as I said before, so let's deal with the tangent first. No, actually, let's just deal generally with it. As I said before, the tangent will have the same gradient as the curve at x equals 0. So the first thing to do is find the instantaneous gradient, dy by dx. Like at this point, you should be quite fluent with dealing with the rule for differentiating. Okay, we don't have to do it from first principles. We can just use the rule. We're going to get 9x squared. If you're not, practice. I'm not bringing out any to the power of a half today or to the minus 1, but it is the same sort of thing. Plus 10x minus 1. I hope it makes sense where all that came from. Okay, that's dy by dx. So let's deal with the tangent first of all. This will have the same gradient when x is equal to 0. So when x equals 0, dy by dx, and actually this is quite simple to find. When I put in 0, I just get minus 1. And you can actually see, like my graph is drawn to scale. First of all, you can see that I've not been quite right with my tangent, because actually minus 1 means they're going to go along 1 and down 1. Actually, the point should go through there. Try this one yourselves. Find the tangent of another cubic, but now at a slightly more complex point. Okay, I'm going to go through it. We know it's going to be a cubic. It might help to, if you haven't done this topic for a while, like if you're coming back to it, to always sort of draw a sketch. This will help remind you. Okay, and this is the sort of line we're trying to find. So we're going to need to find the instantaneous gradient, and then we're going to substitute in x equals 3, and that will give us the gradient of the tangent. dy by dx is going to equal 3x squared, just using my rule here, minus 6x plus 2. Now I want the gradient at x equals 3. And that's going to be 3 times 3 squared, that's 27, minus 18 plus 2, that's going to equal 11. So I've got the gradient of my tangent. And this time I'm even given the y value already, so I can just substitute it in. Y minus 5 equals 11 x minus 3. And it's absolutely fine to leave the answer like that. I've got the equation. I don't have to simplify it anymore. You could rewrite it in the form y equals mx plus c like this if you wanted. Stepping it up a little bit, this time I want you to try and find the normal to a curve, and now it's in terms of a square root. So this, actually I think this curve will look, if I think about my transformations, the negative square root looks like this, and then I've got 8, that's going to shift up, so it might look a bit like that. It doesn't really matter, but just to help me get it correct. And then this time I want the normal at a point, and so that's not going to be the tangent, it's going to be this line here. Okay, well first of all, I'm going to need to find dy by dx. I'm going to need to write y as using indices. So that's the key thing, write as x to the power of a half. Then dy by dx will be minus 3 times a half, that's just 3 over 2, x, and then a half minus 1, that's x to the minus a half. When x equals 4, dy by dx is going to equal minus 3 over 2 times 4 to the minus a half. That is actually equal to 1 over the square root of 4. Because the minus means it's 1 over, the half means it's a square root, and that's going to be 1 over 2, so I've got minus 3 over 4. I've got the gradient of my tangent, not the normal. So, gradient of normal, this will be the negative reciprocal, and all I do is flip it around and make it positive. I also need to work out what y is at this point. So when I substitute in 4 into here, I'm going to get 8 minus 3 times the square root of 4. That's going to be 8 minus 3 times 2. That's going to be 2. 8 minus 6. And I'm nearly there, really close to being there. It's going to be y minus y1, so y minus 2 equals m x minus x1 x minus 4. And there we go. Okay, it's got fractions in, but that is the equation of my normal. It works in exactly the same way as for cubic, so I just need to be a bit more careful differentiating. You could, again, you could write it in the form y equals mx plus c. You could write it in the form ax plus by plus c equals 0, where a, b, and c are integers. These are all expectations as well, potentially, if you could get asked to do that. This is going to be our trickiest example of the day, so I'd like you to have a go at it yourselves first as before. It's slightly different because this time we're given a curve, we're asked for the tangent, but we're not given a point. We're actually given other information. We're told that the tangent is going to be perpendicular to a certain line. So we need to think about that, and my starting point is going to be that line, in fact. So 4y is equal to x plus 4 if I rearrange it, and y is equal to a quarter x plus 1. So the gradient of this line is going to be a quarter. Now I'm told the tangent is perpendicular to this. So the perpendicular gradient is going to equal -4. In fact, the negative reciprocal. And this is also going to be the gradient of the tangent. So I've had to sort of decipher this and figure that out. So I don't have a point, but now I do have one piece of information that I can really use, the gradient of the tangent. We also know that dy by dx is going to equal 2x minus 2, just differentiating this line here. So if I want to work out the point at which the tangent is at, then I need to set the gradient of the tangent equal to the instantaneous gradient. Set 2x minus 2 equal to -4. Then 2x will equal -2 and x will equal -1. And I've managed to get the point at which tangent will be from. Okay, and then I just need the y value. I can substitute that in. It's going to be -1 squared minus 2 times -1, which is 1 plus 2, which is 3. And I've got the key information. I've now got the gradient of the tangent. I've got the x value that it's going through and the y value it's going through. I've got everything I need. And I can just use y minus y1 again equals mx minus x1. Bit more involved. So it's -1. Okay, and again, I could expand it out, but it's absolutely fine to leave it like this. I might just expand it out. It's going to be y is -4x minus 4, but then I'm going to add 3, so I think it's going to be y is equal to -4x minus 1. Okay, just a little picture. I didn't want to give the picture at the start because you wouldn't be given this potentially in a question. But this is what we had. This blue line is the perpendicular line. We've worked out the gradient of the tangents, and you can see that they're perpendicular. We've worked out the point that it goes through, which was -1, 3. That's here, and you can see it all coming together. But slightly different question, same topic. We're just having to now solve equations for dy by dx as well, which I did touch upon last lesson, and there's more of that to come, but not too much today, mainly focusing on finding tangents and normals if you're given a point. One final challenge for today. If I have y is equal to f of x, any function, can you write down the tangent and the normal in terms of f of x and a? Now I'm going to remind you about one thing. Dy by dx is actually exactly the same as f dash x. And if I want to evaluate dy by dx at a certain value, I can actually write this for a, but that can be written as f dash a. Okay, so with those little tips, see if you can have a go. Okay, I've sort of done the main, I've done the main things for you actually. For the tangent, for both lines, it's going to be y minus 1 equals m x minus x1. For the tangent, this is going to become y minus a value, and that's going to be f of a. That's my value of y that I can get if I've got the value of a. And then the value of m is going to be this f dash a, okay, because that's my instantaneous gradient evaluated at a. And then finally, it's going to be x minus a. So you can write down this really nice formula. Not wanting you to learn that or anything, but it's it's a concise way of writing down any tangent. What about the normal? Well, it's exactly the same thing in terms of the y1 and the x1, but this time, remember, I've got the negative reciprocal of the gradient, so it's going to be -1 over f dash a and then x minus a. So again, another very concise way of writing down the tangent and the normal.